Good afternoon, everyone, and welcome to the ISQG YouTube channel. My name is Davide De Biasio. I'm a member of the outreach activity team, and today I'll have the pleasure of interviewing Professor Nick Huggett. At the University of Illinois at Chicago, Professor Huggett works in philosophy of science and on the philosophical aspects of physics, with an interest in quantum mechanics, spacetime, and quantum gravity. Professor Huggett, thank you very much for being here.
Thank you very much for having me. It's great to be here.
I'm glad to hear that. Well, I would start with the first question, like straight away. Can you tell us something about the philosophy of physics? Namely, our audience might not be used to hear this term and might not really know what the philosophy of physics is. So I guess that it might make sense to start by defining who philosophers of physics are and what they do in their everyday life.
I mean, I think the general idea is that physics is not just equations plus experiment. There's also a very strong and important kind of conceptual aspect to it. What do the equations mean exactly? How is it that they're connecting with experiment, which obviously tells you something about what they're meaning. So that's really where philosophical questions come into physics. So I would say philosophy of physics is not just a matter for philosophers and professional philosophers. It's something that many physicists do and is very important, a very important component of physics, whether done by physicists or philosophers. So, when people ask this question, I am still a philosopher. So the tendency is to go sort of historical here and try and think about the history of physics. Modern physics sort of clearly starts around the way we understand it now, sort of starts around in the 17th century with the scientific revolution, and in particular, of course, the work of Newton, but other people at the time. But I would extend that, further back in time to the ancients and to Aristotle, say, and other ancient thinkers. And in that sort of sweep, you can see very much how sort of conceptual issues and mathematical issues come together. For the ancients, I mean, the problem that kind of dominates physics, at least from our vantage point now, post-Newton, was the problem of the planets, understanding the motions, of the planets as we see them in the sky. Ultimately, resolved by Newton in terms of the Newtonian classical gravity theory. For the ancients, this was a problem very much to be solved by sort of geometric thinking, and led to a great deal of thought about, the nature of motion. How do we understand, what is a natural motion? What is a forced motion? Understanding how one thing can act on another. Understanding the difference between matter and bodies and versus space and time. So all these questions have long been sort of thought of as philosophical questions. But I think, the way I see it is these questions are interesting. They do have human interest, but they're also, a lot of the interest in them is trying to understand what these terms mean so that one can produce a theory of physics. So Aristotle certainly was interested in those questions, reacting to the physicists, the astronomers, the geometricians of the day. Newton, it's very sort of explicit in some of his writings. I mean, one of the key contributions of his Principia, the book in which he develops the theory of universal gravity, there's arguments about the nature of space and time, discussions of the nature of matter, different characterizations of different kinds of forces. So thinking about, indeed, methodology in science. So you can study Newton either as a physicist and sort of think about what he did mathematically, but philosophers are also very interested in what he thought about these ideas: space, time, matter, action, and sort of tying them all together, the concept of motion. Obviously understanding what motion is, change of position over time. So you have to have an understanding of what space is. You have to have a thought about what time is. We're interested in natural motions. Newton's first law tells us about bodies carrying in natural motion, how they'll move without forces. His second law tells us how they move with forces. So we need to understand that distinction, the inertial and non-inertial motion, something about the notions of forces. So all those, we can write down things mathematically, but I think we all think about them kind of conceptually. There's a sort of story about how they go together. So that's, so in some sense, Newton and his contemporaries, he engaged in debates about this with Descartes, with Leibniz, with various other thinkers. And one can see that, purely as just sort of philosophical arguing, and because of some of the ideas they had at the time, some of those arguments seem strange to us. But I think if you think about what they were all trying to do, which is develop a theory of mechanics, and as I said, in particular, the motions of the planets are the thing, is the thing that they're really focused on, right? And that's what they're trying to do. That lets you see that the debates they're having are really about how to formulate a physical theory. What are the basic concepts in terms of a theory? Okay, so we can kind of come forwards from there. In the 19th century, discovery of non-Euclidean geometries and thinking about different kinds of geometries. There's a lot of kind of philosophical work. People like Poincaré is very important. Here, thinking about the physical significance of non-Euclidean geometries. So that's a sort of source for philosophy of physics. And of course, many of those debates sort of culminating in special and general relativity and Einstein's thinking. I mean, I think lots of people know about Einstein's thinking about space and time, his thought experiments, his very, that he engages in, the sort of experiments with lightning striking trains to think about the relativity of simultaneity, the kind of reasoning that you have in his papers presenting these theories. It's very much of a kind of conceptual kind to help people think through, to understand what new mathematics, what new ideas are needed and how they're embodied in the mathematics. So again, that's an important, clearly a physicist, but I think doing this sort of philosophical work. And Einstein's work was incredibly, Einstein's work in relativity and in quantum mechanics were very influential on a large group of philosophers at the time, really sort of engaged and changed the way they thought about things. And in a sense, that's the point at which philosophy of physics as a subject done by philosophers rather than physicists is sort of came about. So yeah, okay, that's quite, as I said, going historically and sort of thinking about how I think this has always been a thing, philosophical work in physics has always been a thing, but giving you a little idea about when people who identify themselves as philosophers rather than physicists started engaging with these things.
So in a sense, if I may jump in and recap what you said, and please feel free to correct me if I'm wrong or if I misrepresent your position, but...
Won't hesitate.
You're saying that physics or natural philosophy, or however you want to call it when it's the ancient one, and what we refer to as philosophy of physics have been kind of intertwined since at least Aristotle's and ancient Greek and so on and so forth. Philosophy of physics is kind of involved with making our concepts clear, with conceptual clarity in a sense. But since the revolutions brought about by general relativity, special relativity, quantum mechanics, in a sense, the philosophy of physics became an independent field. It's done by philosophers in deep interaction with physics, but with people identifying themselves as actual philosophers of physics, focusing on the conceptual side of theories. Is that kind of correct?
Yes, no, I think that's right. I mean, part of this goes on with sort of, this has, the story in the background, of course, is the sort of specialization of academics into different, into the kind of fields that we recognize today at the university. I mean, I think that had started happening earlier in the 19th century, that there would be people who were sort of philosophers. I mean, earlier than that, back in Newton, you know, as you say, natural philosophers, it's very hard to make a distinction between somebody's working in physics and somebody who's working in philosophy. Newton's book is The Mathematical Principles of Natural Philosophy. There's a sense in which science and philosophy are kind of one thing, but, you know, universities have become increasingly specialized, partly just because we know a lot more. So it's kind of very hard for any one person to do everything. But yeah, so I think that the specialization and the sort of the existence of people who were philosophers rather than scientists was sort of happening in the 19th century. And in a sense, this was what I'm talking about with relativity. Quantum mechanics is a point at which sort of philosophers, that a bridge was made between the two disciplines that had formed. So I would kind of put it that way. So in a sense, it wasn't a sort of splitting, but more of a sort of rejoining of a split that had already happened.
Okay, so there was a specialization-induced splitting that then was...
Yeah, and you know, anyone who works in a university today will be kind of well aware of the different departments and sometimes how little they talk to one another.
Oh yeah, that's clear. And that's one of the reasons why we're doing what we're doing right now. As you know, then maybe we can get back to some issues concerning relativity and quantum mechanics, because they are relevant for what we're talking about. But here we are on the YouTube channel of the International Society for Quantum Gravity. So I'm forced to ask you what role the philosophy of physics might play in dealing with the issue of quantum gravity. Because let me make my question more precise, because when we're dealing with classical mechanics, quantum mechanics, special relativity, even general relativity, we are kind of dealing with stuff that's being tested somehow, that works, that we are confident with. Well, quantum gravity is much more tentative with alternative approaches, with less clear problems at hand. So what's the role of the philosophy of physics in such a developing field as quantum gravity?
Yes, so I mean, I would say, if anything, the philosophy of physics and, you know, philosophical sort of reasoning about physics, you know, more generally, I want to emphasize it's something physicists do as well as philosophers, is actually most prominent in such a case. I mean, just go back to sort of Einstein, thought experiments about general relativity, say, you know, helped him develop the theory and sort of think about the concepts, how concepts would have to change if you moved, you're trying to move gravity into a relativistic setting, and how exactly to have curved space-time geometry, sort of what that means conceptually. That's sort of there at the front end when he's developing general relativity, and before the famous tests. Okay, that's what he uses to actually get to the point where it can be tested. Similarly for Newton, the tests, he had evidence as he's presenting the theory, but the tests came in, much of the confirmation for Newtonian gravity comes from later astronomical experiments and confirmations of the theory. So it's really when you're having to actually change how you think about things, and actually come up with quite a new sort of framework, sort of a new, there's new mathematics that you're developing. So, not just, a new, in these kinds of cases, you're developing a new theory, a new physics. When it's very new, you're not just writing down, new equations using the same mathematics. You also often need kind of new mathematics. But that's now saying something often profoundly different about the world, and that's where the conceptual questions kind of come in. So there are well-established theories that philosophers of physics work on, and it's clear something like quantum mechanics, which is very well established. There are still interesting and important conceptual issues. But it's also the case that when something new is coming, that's very much part of what's going on. Let me say one more thing about quantum mechanics, since I mentioned it there, and that's kind of a nice example where it is well established empirically. But I'm thinking about sort of conceptual issues. Philosophers have been, long been interested in, well, quantum non-locality. Bell's theorem was a very important issue. Sort of two philosophers of physics that now these issues have manifested in various ways in sort of quantum information theory, for instance. Those, so I think it's not just philosophers finding things to kind of pick apart in a theory, or, well, I could object to this, but why bother? These conceptual objections, even in empirically conceptual kind of questions and questioning, even in empirically well-established theories, really, I think quantum mechanics and quantum information theory and recent interest in foundational questions in quantum mechanics, these are things philosophers have been sort of engaged with, even when physicists weren't, by and large, weren't that interested in them.
Yeah, that's really relevant, and everyone knows that the debate around, for instance, interpretations of quantum mechanics, the actual meaning behind the measurement problem, and so on and so forth, are heated and absolutely contemporary. But focusing a bit more on the issue of quantum gravity, which in the mix is the problem of quantum mechanics with that of gravity, so kind of increases the conceptual complexity in a sense. Can you make some examples, give me some examples of issues that within quantum gravity that can be somehow tackled from a philosophical perspective, some key issues in quantum gravity?
What I primarily have been working on is the question of space-time emergence. So there's a sort of conceptual question here. Quantum gravity theories sometimes tell us that space and time are very, very different, more different, than we think they are, more different than Einstein told us, and perhaps to the point where you wouldn't even think that they were really space and time anymore at all. So there's a sort of conceptual puzzle to sort of understand why the world appears to be spatiotemporal, if perhaps in fact it isn't. That's a question I think that physicists of quantum gravity sort of deal with implicitly. So one of the things I've been working on is looking at how that happens and try to spell out how people react to that situation, try to understand that. So I think that's, in a way, sort of stepping back and giving a broader picture to physicists, to what it is they're doing. I think your question asked whether it was helpful or not. I don't know. I'll let physicists judge that, but it's interesting to philosophers, and it seems a question that engages people. I think there's a number of programs in quantum gravity where physicists feel quite engaged with philosophers of physics on various issues, sometimes because they have sort of historical motivations. They actually find their views sort of inspired by historical philosophy work in various ways. Sometimes because they are, say, interested, they think the measurement problem is relevant to what's going on and to the solution. So that's a sort of there's various ways in which physicists relate what they're trying to do in quantum gravity to work in philosophy and ideas in philosophy. There's various other technical issues. And philosophers of physics run a whole spectrum from from the very philosophical to the more or less just doing physics kind of point of view. So one issue, so there's various technical issues that people have engaged in. Like the quantum gravity community, there are at the moment quite a few philosophers of physics who are interested in black hole radiation, whether black holes truly can be said to have a temperature, what to say about black hole evaporation, information loss, thinking about those questions conceptually. In a sense, yeah, I mean, then it's really contiguous with what many physicists are doing. So that's a sort of range of kind of cases, I think, where philosophers are engaging with physicists and working in issues in quantum gravity.
Thank you very much. Thank you very much. Now, moving a bit towards something you've been working on, which is quite interesting. I'd like to open the issue of quantum gravity and phenomenology, or experiments, if I may call it as you like. Perhaps phenomenology is a bit less demanding than experiments as a term, depending on how you decide to use it. First of all, can we frame the issue? Namely, what's the problem with quantum gravity and experiments in the first place?
So, I mean, the classic way of framing the problem, right, comes from the way high energy physics has been from the point of view of high energy physics, has been incredibly successfully implemented for more than half a century at this point, which is in terms of thinking of a quantum field theory. So we have particles of a certain kind, and we want to study their interactions. And the way to do it is to build big colliders and have exotic collisions happening, and then study the outputs from that. The problem, of course, is gravity is incredibly weak. So the force is very small, and there's a sort of energy scale, the Planck scale, which one could sort of associate with the kinds of energies at which one would expect to see quantum gravity phenomena from that point of view. But that scale would require, a collider. People do these calculations. It's, I don't know, some fraction of of an astronomical unit, the distance from the Earth to the sun. So, that way of thinking is not kind of practical.
Allow me to jump in, just to rephrase it for our audience. You're saying that there's no hope of probing quantum gravity directly in the same way as we probe like Higgs field physics at the LHC and so on and so forth, at least not in a naive way. Is that kind of correct?
Yeah. As long as you put the naive, who knows, maybe that, the hope of, well, we'll talk about the sort of hopes, but if you just sort of thought very crudely, naively about, oh, just do the same thing, then it seems like there's really no prospect of doing any experiments like that. Conversely, just in general, looking around, those sorts of energies don't typically sort of exist, except in very violent events like perhaps the final evaporation of a black hole, or the Big Bang, which are not accessible. So those are sort of problematic. We don't sort of see them occurring naturally either. So did you ask the question about then what happens if we're not naive, or is that just...
No, you can proceed. Yes. I would, my natural question, so I thank you very much for your comprehensive answer, but as you predicted my, and this is quite ironic, we are discussing predictions and experiments. My follow-up question would have been whether there's any non-naive or more hopeful way of thinking about quantum gravity and experiments. Like you, as you said, quantum gravity is expected to become, at least in a naive sense, standard effective field theory reasoning to become relevant at super high energies we cannot expect to probe as we probe like QCD or 3D and so on and so forth. So is there any kind of hope? Is there any subtle way of seeing the issue that might give us some chance to do this anyway?
Yes, okay. So I'm not an expert in all the ways people have been thinking about this, but I can certainly talk about some of them. I mean, one thought that might have occurred to people already is, because I mentioned the Big Bang, say, well, we see the cosmic microwave background, so we do see sort of some early universe sort of clues, and maybe, that's from after the Big Bang, but maybe there are somehow in the CMB traces of something that happened even earlier that are quantum gravitational. So that's one thought, is that one might see, be able to somehow extract evidence from that. There's other people who think in a sort of effective field theory thinking way that we should assume that we won't see anything there, that actually might be a thing to assume, which is depressing as it is. People have been looking at black hole mergers in the gravitational wave experiments to see if they can see signs in there of something quantum happening. There's various other tests people have done looking at various things, cosmological, astronomical signals, trying to put small effects of different kinds together to try to see if there's some characteristic quantum gravity effect. As far as I know, nothing sort of stunning has kind of, and helpful and convincing has kind of come out of that as yet, but that seems the work people want to do. I mean, what seems to happen, as far as I am aware, is when somebody thinks of an effect you might see and goes to look for it, it's usually a null result, and you don't see that. Some quantum gravity effects, although on this kind of effective field theory reasoning, you might think were well outside observation. Some things might be magnified so that we would see their effects. For instance, there's various ways in which, if it turned out space and time were discrete, that discreteness can often show up in much lower energy setting. They might be discrete at the Planck scale, but those effects might manifest in certain kinds of symmetry violations at lower energies. So people hope and look for those kinds of things. But then there's also, I think, because, well, for various reasons, perhaps partly to do with the cost of ever bigger colliders, there is interest in doing more fundamental physics that's at low energies, instead of increasing the energy to try to see more and more fundamental effects. Keep the energy low, but make more and more precise measurements to try to see. I mean, that's the problem. The effects are really small. So do you use more energy to make the effects bigger, or do you improve your apparatus to make it more sensitive to the tiny effects? So that, as far as I can see, is a trend in physics at the moment. And actually, I was reading in Physics Today, in the recent issue, there's a sort of article about some of the labs that this isn't just quantum gravity work, but fundamental physics work, what one would think of as high energy physics work as well. There's a lab here in Chicago at Northwestern that specializes in this kind of thing. So I think, there's various kinds of experiments of that kind that, people are trying. But certainly one part of that is people trying to make experiments measure the gravitational effects of ever smaller things. Some of this, I think, started with experiments to try to see whether the hidden dimensions of string theory were rather bigger than predicted, in which case one might see violations of Newton's law. At millimeter or smaller than millimeter sort of scales, and the thought of trying to do gravitational experiments with really tiny things really close together. And that's sort of developed as a field. But it's developed to the point where, now sort of coming to the point of some work I've done recently, which I think again is sort of in the back of your question. A few years ago, well, that experimental work is exciting because at the same time, people have been interested in studying the quantum behavior of ever larger bodies. The problem there is decoherence. The bigger a body it is, the more parts it has. The more parts it has, the more opportunities it has to interact with the environment, the harder it is to keep it as a closed system. And if it interacts with its environment, it becomes correlated with the environment in an uncontrollable way, and we have decoherence, and it stops behaving in a observably quantum mechanical way. So people have been getting better and better at combating that effect. And, you know, what we have, so here's the things getting bigger from the quantum, you know, staying quantum while getting bigger, and here's things getting smaller as they get gravitational. And what one's hoping, what people are striving for at the moment, is to sort of bring them together. These scales can be brought together. And then, well, the thought is have an experiment where you have quantum objects and measuring, you know, one's measuring their gravitational interactions and the effects of their gravitational interactions.
So allow me to, before you continue, if I may, let me rephrase this thing to see if I understood and in service of the ones who are listening to us. So on the one hand, you have experiments that attempt and actually succeed at preserving superpositions for larger and larger and larger objects like molecules, like big molecules and objects like that. Something which was unthinkable.
Exactly. That was my left hand.
Yes. The objects which we can measure, of which we can measure the quantum behavior, kind of get bigger with time because we get better at preserving the quantum behavior, right? And on the other, measurements of like gravitational effects become more and more precise. So the objects of which we can measure the gravitational properties get smaller and smaller. So in a sense, your hope, I kind of copy what you did with your hands. Like the hope is that the two scales at a certain point will match.
That's the right kind of picture, trying to bring these two together. I mean, the gap is still substantial, but I think on the positive side, the gap has closed a great deal in the last few years. And there's a number of people who are really focused on trying to close the gap right down. You know, people are really working on these experiments. I visited Markus Aspelmeyer in Vienna in the summer, where his lab is working on these things. You know, they're going through the stages to try to make this kind of experiment actually happen. So, you know, his group has been sort of developing the technology to do this for a while. A lot of the recent excitement about this has come up in the last couple of years. A pair of papers came out in 2017 that caught a lot of people's attention and got the community quite focused on this issue. And so thinking about ways of, you know, better experiments that one might do, thinking about it conceptually, trying to think of, sort of alternative kinds of phenomena that could be observed, and also try to understand the significance of these experiments. So I just wanted to say one thing, that, you know, you said that we might measure these, and one uses the word sort of we here. I sort of stand in awe of kind of experimentalists who are in this field generally, of these sort of high precision measurements. Just the kind of care and precision that's needed is kind of mind-blowing, really. I feel that about experiment in general, really. It's just not a thing I could ever be careful enough about, or so we is used in that sense here for sure. So it might be interesting to talk about it. I just mention a couple of or a precursor of this kind of experiment that was actually done back in the 1970s. People became interested in neutron interferometry, so using the wave, taking neutrons produced from nuclear reactors and studying their wave behavior. And early on in that, it was actually realized that if you took a neutron and you put it through a beam splitter, so a single neutron is now following, the filter's not going, you would split it, send one beam horizontally and then vertically around a rectangle, send the other part of the beam first horizontally, vertically, and then horizontally. So the big difference is one's traveling higher than the other in the Earth's gravitational field. This would produce, just because of the potential difference in the Earth's gravitational field, that this would be enough to produce a phase difference between the two packets that, when they were recombined, would produce an observable interference pattern, which was indeed observed. So that's a kind of nice model to sort of have here. That's not a quantum gravity experiment, because the gravitational field is the Earth's, and the Earth is not really behaving in any interestingly quantum way in that case. It's a purely classical field. So one way of thinking, this is not exactly how the experiments would work, but that's the sort of way of thinking of these new kinds of quantum gravity experiments. Something like that, except instead of a classical system like the Earth, you'd actually have another quantum object. You'd have a pair of quantum objects. And because you now had a source that was quantum, you'd have something, that's the thinking. The gravitational field itself would then be in a quantum superposition.
So you would study the interference pattern observed on a probe when subject to the gravitational field sourced by a quantum object. That's the kind of...
Yes. So that's sort of conceptually how you do it.
Okay.
Technically, what people are actually interested in is, it's a slightly different idea. But you'll have two systems like that, and you'll measure that they become entangled because of their gravitational interaction, and it's actually the entanglement between them. And so you'll find that there's quantum correlations between them, and that can only happen if the gravitational field behaves in this quantum mechanical way. Or a little more carefully, they won't become entangled if there's only a classical gravitational field between them. So, but yeah, so that's the idea. So.
That gives some kind of hope, right? For the people listening to us, I'm sure many of them are students desiring to enter the field of quantum gravity phenomenology and experiments. So hearing that there's a chance to come up with more nuanced and subtle experiments to test quantum gravity is surely nice and reassuring for them. And
yeah, but I think, like I say, the basic idea of what's kind of, what's happening is quite straightforward in elementary quantum mechanics. There's sort of more subtle issues when you think about how exactly what it means to say gravity is behaving in a quantum mechanical way here. And there's been a certain amount of debate about that I recently have a little book out with Mike Schneider and Niels Linnemann, where one of the things we talk about is the debate between exactly how to describe what's happening in the experiment, and to what extent, what it means to say that it's quantum mechanical. I think one thing to think about is mathematically, conceptually, there's a lot of similarity between gravity and electromagnetism, right? And the character, we all learned in, certainly in the bachelor's, probably in high school, the characteristic quantum phenomenon of electromagnetism is the production of a photon in an atomic, when an electron changes its energy level in an atom. And that's not but it's not going to be possible to measure individual gravitons in this way. So one has to have a sort of more subtle effect of gravity, somewhat more indirect than detecting individual gravitons. Although that's what's happening as well. It's the same. But they're very similar mathematically. This at a conceptual level, the picture's pretty similar.
And in this sense, if I understand correctly, your work if I can call you and identify you as a philosopher of physics, and yours and of your colleagues clearly, has been that of giving some kind of overview picture of what people are doing and try to put some conceptual order in the kind of debates around the quantum gravity experiments and making them, in a sense, organized, if I may. Like, is this an appropriate kind of organizing them in some clearer? Because clearly, when this is important to remark, when scientists do what they do, they do not always take the step back perspective that a philosopher might have, right? So your position is that of an observer of what's happening in labs, and somehow someone who attempts at putting order in what people say and think and do there. Is that correct?
Yes, I think that's part of it, and I think for physicists that's probably a good way of looking at it. I mean, I think we also identified some questions that philosophers have sort of thought about, and that come up in there as come up as well. So in some sense, what we're trying to do is when people have disagreements, what exactly is it that they're disagreeing about? Because it's not always, I think, excuse me, sort of obvious to one another what it is the other person's assuming. So trying to dig back a bit and sort of think about the different starting points. And in this case, one of the key things has to do with sort of everybody, well, not everybody, but many people would sort of agree that the underlying theory is, as we're sort of saying, is this sort of quantum field theory of gravity. But then there's different ideas which somewhat come down to whether you think about that more from a quantum field theory point of view. It's a quantum field theory of gravity, but do you put the emphasis on the quantum field theory, or do you put the emphasis on the gravity? And that leads you to slightly different pictures about what it would be to see gravity as quantum, for instance. So,
yeah, the history of quantum gravity is the history of of an attempt to merge two quite distinct perspectives and traditions, right? The one coming from GR and from particle physics, if we can call it like that. So I can see where this goes, right?
Yeah, I mean, this is interesting because when the equation you sort of start with, which is, you basically start, if you think about starting with, so general relativity for small perturbations, because there's not going to be a lot of gravity. So you have sort of, that's linear gravity, and you have the first order perturbation, smallest contribution, and you think, okay, that's it's a gauge theory, and I'm going to quantize it. Even though they agree with that, it still sort of diverges. Usually you think about the divergence when you're headed the other direction, and because you have, even linear gravity is, you have to make approximations to get to this case. You have to treat it and how you go about constructing those approximations is what leads to the difference. I think what you were indicating is really going the other way. Well, we agree on, this is what gravity is going to look like at low energies. But when we go to high energies, that's where we disagree. But I guess you disagree as you go to lower energy, even lower energies as well, but in a kind of more subtle way. I mean, you don't disagree about what's going to happen. It's just how to describe it.
Okay, that's an extremely interesting take.
I hadn't quite thought about it that way. And I'm sorry,
yes,
there's obviously a number of details there to sort of talk about what that actually looks like. But yeah.
No, but I would say that you made your case quite clear, and I hope my personal interest in the philosophy of physics did not bias my interviewer too much. Now, may I ask you some more personal question before I free you from this burden? Can I?
Of course.
Okay, because this might be quite useful for young audience of students. What led you into the philosophy of physics in the first place? Like, why did you get interested in it? If you know an answer. I mean, not having an answer is a perfect answer that might relax people a bit.
No, I know personally there was a very kind of clear path, and then I'll say some more general things about why that path was why I was happy on that path. So in the UK, I think it's still the case, but especially when I was in high school, and so in the 1980s, you really the system was set up so people would specialize into science, math, physics, chemistry, and maybe extra maths, maybe extra physics. A lot of people did something like that. Or you could go and do sort of English, history, economics, or something like a very kind of much more humanities and social science route. So I went on the science route, but much as I enjoyed all those things, I missed doing the humanities part of it. And so when I was thinking about going to university and looking through catalogs, I discovered there were these courses in physics and philosophy, and that's exactly what I want to do. And I was exactly right. So I don't know, I was just very fortunate to kind of get into it that way. I mean, I think in a broader way, what was going on is there's quite a lot of philosophers of physics who start off as physicists, and indeed as sort of, on the physics side for longer than I did, through their bachelor's degrees, through master's degrees, sometimes through PhDs in physics, and then, work their way to philosophy. But I think, what a lot of us have in common is we're always the kid who sitting there sort of, well, why you're taught how to do something in physics. And I think people who are good at physics are very, very good at generalizing physics problems. You show them how to do a couple of physics problems, you tell them a few things, and then they're just very, very good at generalizing that and expanding that idea, and just somehow intuitively seeing what idea they're being taught. But I think there's others of us sort of sitting there well, we'd much rather hear an axiom or a kind of rule here that sort of explains what it is with, what the rule is, write it out and understand why it's justified. And that's a lot of what philosophy of physics is saying, I can see you guys that, you know what to do, and I can see write papers, and I think, you know what to do, and clearly it's working. But we're really and that's where the conceptual side comes in. I want to sort of understand exactly what this rule is more precisely and understand how it's justified. I think that's, yeah. So that's, I think, a fairly common kind of story. It's like, we love physics, but we kind of want to have certain things made more explicit.
Well, and then all the people listening to us that have this kind of tendency will know what to do with their lives. Now, Professor Huggett, I want to profoundly thank you for having been here today and for our interview. I hope you're happy with it. And
yeah, this has been a great deal of a lot of fun. So.
Yeah. We discussed a lot of super interesting things, and we are super happy like having someone like you on this channel. And if I may, I'd like to thank all the people listening to us up to this point today, and goodbye.
And I will thank them too as well. I hope there's been something interesting here. Thank you, David.
Thank you.